Hi there. Today I'm going to try to answer the question of why is a vector space important in engineering. So we have different types of data, including physical data coming in from real world scenarios like images, sounds, EKG signals in biotech, aerofoil from airplanes. And then we have digital data, which can come from enterprise resource planning software, movie recommendations, product recommendations, and so on. Now, the way we represent this data is different for physical and digital data. So for the physical data coming in from sensors, we use signals to represent them, which go into computer code in the form of functions. On the other hand, the discrete data coming in from the digital systems are represented using statistics, and then they can be characterized by using some measure of central tendency to define them. And this measure will often depend on what metric is useful for studying a specific problem from that data. Now, why are these two representations important in terms of signals and central tendencies? Well, these functions are often orthogonal to each other in an appropriate representation. And also these statistics are uncorrelated to each other when represented in an appropriate representation. The concept of orthogonality and uncorrelatedness is the same, and I've tried to write it intuitively in red here, which basically means that independent properties of data are preserved by representing them on perpendicular axes. And another very intuitive way to think about this is by representing the data in this way, we're sort of preserving all the ingredients that you need to make a cookie, and you're not losing any of the ingredients. So this is the central characteristic of a vector space representation, which is preserving information by using the concept of orthogonality. Now, what this does is it gives us an efficient way of approximation or calculation for different types of operations that we would want to do, which include decomposition, projection onto subspaces, which is common in dimensionality reduction. It makes it easy for computing eigenvalues and eigenvectors. It makes our matrices diagonalizable, which is an essential component for the Fourier transforms and the convolution operation. And so one specific example of decomposition is singular value decomposition for, let's say, the digital discrete type of data, and then modeling using cosine transforms and Fourier transforms, which are orthogonal bases, which we use for signals, which will be modeled as functions in a vector space. So hopefully the notion of why vector space is important in engineering is a bit clear after this video. Thank you.